Our next example is more advanced. It is the Chu-van-der-Monde identity once again. So recall the Chu-van-der-Monde identity, theorem 231 in lecture 15, which tests the following. Let n and n and x and y be two real numbers. Then x plus y choose n equals sum from k equals 0 to n, x choose k, y choose n minus k. How do we prove this bijectively? So first, we assume that x and y are in n. We will explain later how to get rid of this assumption. Because, of course, if x and y are not non-negative integers, you cannot hope to give combinatorial interpretations for the left and right-hand sides. These are not integers in this case. So you assume that x and y are in n, so these are integers. And there is a hope of a bijective proof. Once again, it's a liquid boundary between between bijection and double counting. I will actually explain this proof in terms of double counting and later explain how this is also a bijection. So let Q be the set 1, 2, ... x union -1, -2, ... -y. So it has x positive entries elements and y negative elements. How many n element subsets does Q have? We answer this question in two ways for a double counting proof. The first way is easy. Clearly, Q has x plus y choose n many n element subsets. Why? Because it's an x plus y element set, and the number of n element subsets is x plus y choose n by the combinatorial interpretation of binomial coefficients. But the second way is more interesting. So we can choose an n element of Q as follows. First, we choose how many elements of this, say, an element subset, and then we call it S. First, we choose how many elements of S will be positive. Let I be this number. So S will have I positive elements and n minus I negative elements. And actually, why am I using I? I'm going to call it K, because this will be the K is the sum later on. And notice that K, of course, is between 0 and n, because, well, the whole set will have n elements, so the number of positive ones will be between 0 and n. Okay, having chosen that there will be K positive elements, we actually choose those K positive elements. So we choose the K positive elements of S. And the candidates are 1 up to x. So we need to choose K elements out of 1, 2, ... x. And we're choosing a subset. So the K elements have to be distinct and their order doesn't matter. So the number of ways to do this is x choose K, because we are choosing a K element subset of the X element set 1, 2, ... x. And finally, we choose the n minus k negative elements of S. And the number of ways to do this is, well, the candidates are -1, -2, ... y, and we have to choose n minus k of them, so this will be y choose n minus k. Now, this is not a dependent product situation, because depending on which k you choose, those numbers will be distinct. So instead, this is a situation for the sum rule. So the total number of ways to perform this construction is sum from k equals 0 to n. And the sum is because of this first choice. There is you can choose any k from 0 to n, so you have to sum the number of options for each of those k's. And then in the second step, you have x choose k options, And in the third step, you have y choose n minus k options. This is a product rule situation. Okay, so now we are on familiar grounds. So we have thus found two answers to the question, how many n-element subsets does Q have? And these answers are, first, on the one hand, we got this, on the other, we got this. But it's the same question, so it has to be the same answer. So comparing these answers, we obtain that these numbers are equal. Okay, now I have not fully, so I have proved this theorem only under assumptions that x and y are non-negative integers. So this proves the Chu-van-der-Monde identity for all x, y, n. Now we can generalize it to x, y, and r as follows. First, keep x fixed and use the polynomial identity trick from several lectures ago. I think it was lecture 16. Nope, it was probably lecture 14 or something like that. Yes, lecture 14. To generalize from y in n to y in r. Because it's a for fixed x, it's a polynomial. This is a polynomial in y, and this is a polynomial in y. If they're equal on the non-negative integers, they must be equal everywhere. Okay, now the shoe is on the other foot. Now we keep y fixed, and we use the polynomial identity trick again to generalize from x and n to x and r. So as if you want to know the details of this, there are they can be found in 263 of the old notes for details. So the theorem is proved. Okay, so this was a proof by double counting. How do we make it into a bijective proof? Basically, instead of, well, we have to reframe it. Instead of counting the same things in two different ways, we now have to count two slightly different things and use the bijection principle. So where is the bijection principle applied? The bijection principle appears where you basically restate the question of choosing an n-element subset of Q as the question of choosing a k-element subset of 1 up to x and an n minus k element subset of minus 1 up to minus y. So essentially, what we constructed above is a bijection from pk of q and pn of q, and I remind you that this notation means the set of all element subsets of q, to pk of 1 up to x cross, so Cartesian product p n minus k dot minus y. However, what is k? The k is, there is a different k depending on the subset, because k is a number of positive elements. It's not the same every time. So actually, you have to extend this notation a little bit. I'm going to call this p and k of q, which is the set of all n element subsets of q with k positive elements. And I mean exactly k positive elements, not at least k. So, and this Cartesian product is the set of all pairs xy, where x is a k element subset of 1 up to x, and y is an n minus k element subset of minus 1, minus 2, dot, minus y. And what this bijection does, it basically cuts, it breaks up a subset of Q into its positive part and its negative part. So it sends each subset S in P and KQ to the pair S plus, S minus, where S plus equals the set of all positive elements of S, and S minus equals the set of all negative elements of S. Alternatively, you can write this as S plus as S intersect with the positive part, and this would be S intersect with the negative part. And it's pretty easy to see that this is a bijection, because if you break up a set S and here into S plus and S minus, it's basically by definition that S plus has K elements and S minus has N minus K. If you want to invert this map, you just take the union. So if you have S plus and S minus, you can of course combine them back into S by taking their union. So there is an inverse map, and so it's a bijection. So the bijection principle therefore yields that the size of this set equals the size of this Cartesian product. But now we recall the product rule. So the size of the Cartesian product is the product of the sizes. So we're using the product rule here as well. And this is, of course, just the K element subsets of 1 up to X. So there's number is X choose K. And this is the N minus K element subsets of -1 up to -Y. So the number is Y choose N minus K. And let's not put the dot here. Okay, so remembering what this P and K of Q is, this is the set of all N element subsets with exactly K positive elements. So this is the number of such subsets. This is X choose K, Y choose N minus K. However, each N element subset of Q has exactly K positive elements for a unique value of K. Because of course it has some number of positive elements, and that number is between 0 and 1, between 0 and n. So, and that number is unique. So this K is unique. So by the sum rule, the number of N element subsets of Q equals, we can break this apart according to the number of positive elements, and we get the sum of the number of N element subsets of Q with exactly K positive elements. But as we just showed, this number here is X choose K times Y choose N minus K. So this is the second way in which we computed this number. The first way is just saying that this is X plus Y choose N. So X plus Y choose N, which follows from the combinatorial interpretation of BC's, binomial coefficients. Since Q is an X plus Y element subset, set, we obtain the equality that we want. So, of course, I'm selling you old wine from new bottles. This is the same double counting proof, just restated in bureaucratically, pedantically formal bijective language. But guys, there will be several more complicated situations if you do combinatorial research, where this language will give you a lot more certitude than talking about double counting. And even more important, it's reassuring to see that the strategies not only prove the same theorem, but they're actually just the same strategy in two different cases.